Good. So, morning, everybody. All had a good night's sleep after the beautiful view we got yesterday from the tower. And it's a great pleasure to introduce the first speaker of today, Bernd Sturmfels from Leipzig and Berkeley, who will give us a view on the geometry of dependency equilibrium.
Yeah, thank you very much. Thank you for coming early after the party. So I'd like to tell you about a joint paper with Iram Portakal. So Iram is a postdoc right now in statistics at the Technical University in Munich. And the paper is about to appear in the birthday volume for Giorgio Ottaviani. And there'll be lots of tensors. So let me start with the basics of game theory. So games in normal form are specified as follows. So we have a game with n players, and each player has a collection of pure strategies they can select from. So the ith player has his or her pure strategy, and I'm calling 1, 2 up to di. So the ith player has di pure strategies. The normal form game is given by n payoff tables, one payoff table for each player. And the payoff table is a tensor. So xi, the payoff table for the ith player, is a tensor, n-dimensional tensor of format d1 by d2 up to dn. So every player has one of these payoff tensors, and they all have the same format. The entries are real numbers, and the interpretation is that a particular tensor entry in position j1, j2 up to jn. So this is the payoff for the ith player, assuming that j1, j2 specify the choices made by all the players. First player chooses pure strategy j1, and these real numbers, they can be positive, so it could be reward, or negative, or punishment. So this is a real tensor. So we have n-dimensional tensors that specifies the game. So of course, if n is 2 in a two-player game, we have payoff matrices. So it's a simple example. A couple decides which concert to attend, or they want to go together and either listen to Bach or Stravinsky. So there are two, they have the same pure strategies, Bach or Stravinsky, so everything is 2. And let's say they really want to go together. They don't want to go, nobody wants to go alone, but the first player has a slight preference for Bach, and the second player has a slight preference for Stravinsky. So we have these diagonal matrices for the payoff. Now, how should they decide? Well, the solution will be a mixed strategy. So the way this works is that you mix your options. So the mixed strategy, the solution of the game, this will be a real 2x2 matrix with the non-negative entries that sum to 1. And these are probabilities. So a Pij is the probability that player 1 chooses concert I and player 2 chooses concert J. Right? So that's the outcome of the game is a probability distribution, the optimal or good or happy distribution that they choose based on the payoffs. So in general, so as I said, the choices are probabilistic. So you should think about the players as random variables with state spaces bracket d1 up to bracket dn. So bracket di is the set of the n first positive integers, 1, 2 up to di. And they somehow collectively choose a mixed strategy. And the mixed strategy is a joint distribution that's also a tensor of the same format, but this now has positive entries. So for simplicity, I will assume in this talk that all the entries are strictly positive. They could be non-negative, but let me assume that they're positive. The interpretation now in this payoff is that Pj1, J2 up to Jn, a particular tensor entry, is the probability that the player 1 chooses J1 and so on. Player 2, J chooses J2. Now, given the game, given by the payoff matrices X, and given the joint distribution P, we can compute the expected payoff. And the expected payoff is simply the dot product of the vectorization of the tensor P and the tensor X. So I'm summing over all possible outcomes, d1, d2 up to dn, and I multiply the payoff by the probability that this happens. So this is the expected payoff for the ith player. So each player has an expected payoff, and the ith player, of course, wants to have their expected payoff as large as possible, right? So the goal is everybody wants to sort of, maximize their profit, and so they want to have their payoff as large as possible. Well, how to make everyone happy? Well, somehow the idea is that we want to reach an equilibrium. Right? So the idea is that everybody makes their choices, they see what's my expected payoff, and somehow we want to say, well, I can now at this stage not change my situation and make it better. And so somehow there has to be a notion of equilibrium. And so given a fixed game, so given a collection of n-dimensional tensors, the set of these equilibria is a subset of the probability simplex. And this is the probability simplex of dimension d1, d2, dn minus 1 with coordinates p. Okay? So I've been vague so far by what I mean by an equilibrium. There's some notion of equilibrium, and given a fixed game, the set of all equilibria are a subset of the simplex. And we want to study this. Now, of course, me being me and A, I represent the A in POEMA. So therefore, this will be semi-algebraic or varieties or something like this. Okay, so there will be some algebra. Now, what kind of equilibria? Well, today I'm going to put the focus on the following notion of equilibria. That's the notion of dependency equilibrium. So I'm going to say a tensor P in our simplex is a dependency equilibrium for the given game if the following condition holds. If the conditional expected payoff of each player I, so for the ith player, in fact for every player, does not depend on her choice. Okay. So here, let's say the ith player chooses K. Now, conditioned on that choice, the blue formula is the conditional expected payoff, right? It's the same sum as before. So it's a similar sum as the expected payoff, except here for the probability, we take the conditional probability conditioned on that the ith player chooses K. So this notation P0000K plus 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 means I'm summing out all n-1 coordinates except I fix the kth coordinate, right? So this denominator, which by my hypothesis is a positive number, so I can divide by it. So this is just the probability that the ith player chooses K, and then this ratio is the probability of making these choices given that she chose K, and then this blue thing is the conditional expected payoff. And I want to say this is the same if she had chosen a K prime. So we prior this for every I, and then for all choices K and K prime, the ith choice a player could make. Okay, so this is one definition of equilibrium, and that's the definition we're going to work with primarily today. Now, the first thing that we're going to do, since I assume that things are positive, don't lose anything if I clear denominators. So I look at this equation, right? So here I'm saying this rational function in the P's is equal to this rational function in the P's. So after I clear denominators, I obtain a homogeneous quadratic equation in the P's. Remember, the x's are given and the P's are unknown. They are decision variables. So now we have a system of quadratic equations, one for each I and each pair K, K. Okay, so these quadratic equations, they have a zero set. I'm going to call that the Spohn variety, and the Spohn variety is just the zero set, the solutions of these equations. And here I'm doing the usual thing we do in applied algebraic geometry. We work in a complex projective space. So since there are many students here, and maybe you haven't seen this so often, so algebraic geometers, when they work on an applied problem, they take a problem and they make it easier, progressively easier in 3 steps. So we're given a problem that involves real numbers and inequalities and equations. Step 1, we throw away all the inequalities. Okay? Now that certainly makes the problem easier, right? Now, second thing we do, we replace the real numbers by the complex numbers. Now, that makes the problem easier because now polynomials have roots and so on, right? And the third thing we do, replace affine space by projective space. Now, any two lines in the plane meet. Any two conics have 4 points. So after those steps of simplification, the problem is so easy that maybe even algebraic geometry can contribute something, right? But of course, we're bearing in mind that in the background, there's a real problem with inequalities, and we have the expertise of the 14 fantastic POEMA PhD students we saw in the video last. But we're going to simplify now and focus on the equation. So we're going to look at the complex projective variety here in this projective tensor space of dimension d1, d2, dn minus. Now, many of you will be familiar with another notion of equilibrium, a more familiar notion called a Nash equilibrium. And the observation or proposition is that the Nash equilibria are precisely the dependency equilibria of rank 1. So if this tensor P, the solution happens to be a rank 1 tensor, then we call that a Nash equilibrium. So geometrically speaking, the set of Nash equilibria, complexified, say, is the intersection of the Spohn variety with the Segre variety, and the Segre variety is the rank 1 tensor. So the decomposable tensors that we've seen a couple times this week. So how to think about this proposition? Well, if you knew before coming in this morning what a Nash equilibrium is, then that's a proposition. If you didn't know what a Nash equilibrium is, then that's a definition. Okay, so Nash equilibria independence, rank 1 tensors, but here we have a sort of a notion that we don't have independence. That's why it's called dependency equilibrium.
Sorry, is it true that the ideal becomes a binomial in this case?
No, in the Nash case, no. I'll say more about Nash equilibrium in a second. Okay, so. In fact, right now, I think that's the slide on Nash. So I assume somehow that you've heard about this or seen this before. So this is a quick reminder about Nash equilibria. Well, Nash's important theorem from the 1951 says they always exist in the closed simplex. So using fixed point theorems, topological fixed point theorems, Nash argued 70 years ago that for any payoff tables X, there's at least one Nash equilibrium, but in the closed simplex. So here I said the P's are positive today, but if I allow them to be non-negative, then Nash guarantees at least one Nash equilibrium and therefore at least one dependency equilibrium. Now, to find them, from my perspective, we're solving multilinear equations of degree n-1. On n player games, you have to solve, multilinear equations. So for a 3-person game, you have to solve a bilinear equation. For a 2-player game, you have to solve linear equations. Okay? From an algebraic perspective, and only from the perspective of A in POEMA, 2-player games are not interesting. Right? 2-player games are linear algebra. Now, of course, 2-player games are very interesting because there's still a combinatorial complexity. So there's still a lot of combinatorial complexity even in the 2-player game. But once you resolve the combinatorial complexity, then 2-player games, just like linear programming, becomes linear algebra. And therefore, we do not see non-trivial algebraic degrees and algebraic structures. However, as soon as we have 3 or more players, then we have higher degree equations, and they are interesting to solve. So what kind of equation? Well, first of all, the number of solutions is finite, but there's a literature on how many there are. So McKelvey and McLennan 25 years ago applied the Bernstein-Kushnirenko approach, and they showed that the complex count for the totally mixed Nash equilibria has a beautiful formula as a mixed volume of simplices, so it's a very beautiful polyhedral formula. But on the other end of the spectrum, there's Dada's universality theorem. So she showed that every semi-algebraic set is the Nash equilibrium of some game. So Kash, if you give me your favorite semi-algebraic set defined by polynomials with integer coefficients, then Dada or I can make for you a 3-player game such that the set of Nash equilibria of my game is your semi-algebraic. So we have universality in that case. So this, of course, can be cast as a complexity result. But so in general, things are very nice. Right? For general game, there are finitely many Nash equilibria. We can compute them using polyhedral homotopy, say. But of course, if an adversary gives me a complicated game, then the set of Nash equilibria will be complicated. As I said, for two players, after deciding where you are on the boundary, you have to solve linear equations. Now, I like this topic a lot. So around the time when Ruchira wrote a dissertation, I had a connection to the movie a little bit, The Beautiful Mind and Russell Crowe and all that. And so I took this as a chapter in the book that I wrote called Solving Systems of Polynomial Equations. So there's a chapter called Polynomial System in Economics. And I think this is still a nice introduction of 14 pages. At the time, the software for solving these equations was PHCPAC, but now in algebraic geometry, we're using Bertini or homotopy continuation.jl, as you will learn at the Amsterdam school that Monique advertised yesterday. Okay, so that's any questions about Nash equilibrium? Yeah.
So do three-player games suffice?
Yes. So for the universality, three-player games suffice. Also, n-player games with two choices will also, with binary choices will also. You can either have a 2 by 2 by 2 by 2 game, or you can have a big by big by big tensor and with three players. But again, sort of wearing my algebraic geometry hat, we're going to focus on generic games. So we're not going to look at these special games, but we'll sort of try to understand what's going on in general, or general payoff tensors. Okay, so this was a review of Nash equilibria, but as I said, they are special, right? So Nash equilibria arise when players make independent choices. So if we have two players with two choices like Bach and Stravinsky, being independent means you are on this quadratic surface. So this quadratic surface, the Segre surface, variety defined by a 2 by 2 matrix, 2 by 2 determinant whose entries are P sub Bach-Bach, P sub Bach-Stravinsky, P sub Stravinsky-Bach, and P sub Stravinsky-Stravinsky. So this 2 by 2 determinant defines this surface. But there are many other models. And as I said today, we're going to focus on dependency equilibria. Now, of course, game theory and equilibria is a very interdisciplinary subject, right? So this is studied in mathematics, economics, operations research, statistics, of course, very much in computer science, but also in philosophy. So the motivation for this work actually came from a philosopher. So I defined the Spohn variety, and the Spohn variety is named after Wolfgang Spohn, who is a prominent philosopher at the University of Constance in Germany. Some of you know this university. And he wrote a paper that was published in 2007 in the journal Philosophy of Science called Dependency Equilibrium. And the argument is that Nash equilibria can have undesirable or counterintuitive properties. So philosophers are very interested in this. So they're interested in things like prisoner's dilemma, right? So how does human behavior actually work? And so this is a concern also in philosophy. And we picked up on this work by Spohn. And so he defined this, right? Recall the definition. So dependency equilibria says that the conditional expected payoff of each player is independent of her choice. Now, dependency equilibria require non-linear polynomials, even for two-player games, right? So for Nash equilibria, in the independent case, things become linear for two players, but even for two players, dependency equilibria require non-linear polynomials. So I'm citing from Spohn's articles on page 779. He writes the following. I call this a warning about nonlinear algebra. He says the computation of dependency equilibria seems to be a messy business. Obviously, it requires one to solve quadratic equations in two-person games. And the more persons, the higher the order of the polynomials are. The higher the order of the polynomials we become entangled with. all linear ease is lost. Therefore, I cannot offer a well-defined theory of dependency equilibrium. Now, when he writes that all linear ease is lost, that makes it interesting for us, right? So I'm in the nonlinear algebra group at the Max Planck Institute. So precisely the loss of linear ease makes this an interesting structure for us to study. And Ettore is already smiling. So here's the paper, right? So it's a beautiful read. So I really like to. So there are almost no formulas, right? So he introduces dependency equilibria. So he says, in this note, I'd like to present and briefly discuss a new equilibrium concept for game theory. When it occurred to me 24 years ago, I put it aside because it seemed to be of doubtful sense, and so on and so on. The driving force is the prisoner's dilemma. And as I said, he is a senior person at Konstanz in Germany. Right? So he introduced dependency equilibria, and this is the topic of this lecture. Okay, and this I'm citing here, it's covered right now. So he said, let's formalize this idea. So he discusses this for two tables, and then he gives the definition. So P is a dependency equilibrium if and only if for all I, and the corresponding holds, So in a dependency equilibrium, each player maximizes their conditional expected utility with whatever they do with positive probability according to the joint equilibrium distribution. So what we're now going to do is we're going to take these words, this wordy, and on the previous slide, green definition, we're going to turn it into determinantal varieties. Okay. So let's do the following. So for each player, for the ith player, I'm now going to define a tall, skinny matrix with di rows and 2 columns. And in the first column, I'm simply putting the probability that the probabilities for that player to choose the various choices, right? So in the first column in row K, I put P plus plus K plus plus plus. And just as a reminder, this is the sum. I'm summing out, all possible states where there's a plus. It's just the probability that the ith player chooses K. And then on the right side, I put the numerator of the conditional expected utility, right? So the conditional expected utility is this right entry divided by the left entry. So therefore, dependency equilibria are the points in the simplex where MI has rank 1. So each player has a matrix that is a tall, skinny matrix with 2 columns. And the variety says that this is a rank 1 matrix.
Sorry, why in this sentence that you cited, it says higher order polynomials in the all quadratic?
Yeah, he's right. I mean, so this is one way sort of naively clearing denominators. I think he sort of had a different way of resolving them, but they're quadratic. So from my perspective, they're all quadratic.
But with multiplayer games that you introduce polynomials of higher degree, not for 2-player games, but for higher.
No, it's even for n players. These will be quadratic polynomials. They're just the 2x2 minors of this matrix. I think Kaj is right. Okay, well, in any case, all linear ease is lost. Okay, so dependency equilibria are points where each MI has rank 1, and we call this the Spohn variety. So again, Vxx is a game. Vx is the Spohn variety, which is the complex projective variety. But of course, in the application, we're interested in the real positive points inside the simplex. So let's go back to Bach and Stravinsky. So we have a 2x2 game. Then we have a payoff table Aij, a 2x2 matrix, and the second player has a payoff table Bij. Then the corresponding tall and skinny matrices are not so tall, right? So M1 in the first column, I simply have the sums. I have the row sums of the payoff probabilities. Here I have the column sums, and then here I have the inner product, the same version with the Aij, and over there with the Bij. These are the matrices, and I'm interested. So the A's and B's are fixed real numbers. and I'm interested in the rank 1 condition simultaneously on this matrix. So Vx, the Spohn variety for a 2-player game with 2 choices, is a curve in projective 3 space defined by the vanishing of these 2 2x2 determinants. So curve in 3 space defined by 2 quadratic polynomials. Okay. Let's see a picture. So here it is actually for Bach and Stravinsky. So in the very special case where the A matrix was a diagonal matrix with entries 3 and 2, and B was the diagonal matrix with entries 2 and 3. Here's M1 and M2, right? So, so here is the picture inside the probability tetrahedron. So in this example, in this very, very special game, so we get this curve of degree 4, and it breaks into 3 components. There's a straight line that's just spanned by one of the edges of the simplex. Then there's another straight line that cuts through the middle of the tetrahedron, and then there's a parabola that does not, it's outside, it doesn't meet the interior of the tetrahedron. So in this case, our quartic curve for this very special game, the special Bach-Stravinsky game, the quartic curve degenerates. Now here, this black curve, in this case, intersects the Segre surface in exactly 1 point, and that's the Nash equilibrium. Remember, Nash equilibrium are dependency equilibria that have rank 1. This is the unique rank 1 distribution here, and that's this green point in the middle. And BS means Bach and Stravinsky. Now, of course, when you see these equations, when you see quadratic equations, or any system of polynomial equations, you do not go to Mathematica and say solve, right? But you remember what you learned in algebra. You go and ask a slightly more sophisticated question. You ask, for example, for a primary decomposition. So the ideal generated by our 2 quadrics has this primary decomposition. So this is the 1 line. That's the second one, is the relevant line that sticks through the middle. I'm sorry, that's the last one. And then this is the parabola that's irrelevant. So in this example, this last line is the one that sticks in the middle. So, so this is the Spohn variety, is this black curve. The set of dependency equilibria is its intersection with the open simplex. And then the Nash equilibrium is the point in the middle. Okay, so this is Bach. Yes, right.
This Bach-Stravinsky game could be symmetric, right, for player 1 and player 2, but somehow the matrix that you're producing for Nash equilibrium doesn't seem to be symmetric, and this bothers me. But it's probably due to my ignorance.
That is a very, very good question. Okay, I have to think about it. So I have to double check the calculation. Yes.
But this one is unique. If it is unique,
Yeah, yeah. So what's going on here? So it is unique.
Why you say symmetric? I don't understand.
I mean, everything about player 1 and player 2 is the same. You know, it's 2-3 or 3-2. So there should be some symmetry, right?
No. But this symmetry is different, right? So this 9 is the product of 3 times 3, and this is the product of 2 times 2, right? So there's an asymmetry the way they're distributed in the diagonal. So I think it's correct. Okay, you have to think it's right. So this is really, so this is really, this 9 is the product of the upper left entry in one payoff table times the lower right entry in the other one. That makes 9. And the other one around is 2 times 2, it makes 4. So I think it's
The 2 players are not symmetric from the data, I guess. You know?
So there's a simultaneous swap, right? If you swap the players and the composers at the same time, then there's a symmetry. But if you, but if you just swap one, there is. Okay. Good. Yes, question.
Sorry, can there be other real solutions to this Nash equilibrium, to the equation that define Nash equilibrium?
Yeah. Well, not in the 2-player game. So remember, in the 2-player game, we have linear ease, right? So in the 2-player game, we're solving linear equations, and a linear equation, if it has finitely many solutions, has only one solution. But of course, with the 3 or more players, many, many interesting things can happen.
and even positive.
Yes, yes, yes. Even that, so this universality theorem is for positive. But you give me your semi-algebraic set, I'm going to make a game that has, you know, your semi-algebraic set as the Nash equilibria inside the syntax. Okay. Let's talk a little bit about three players. So here they're called Adam, Bob, and Carl. Each has binary choices. So Adam has a 2 by 2 by 2 payoff table A. Bob has a 2 by 2 by 2 payoff table, and so does Carl. And now their matrices are again 2 by 2 matrices. I have 3 of them, right? And now, you know, the first column, these are just the probabilities. So for the choices of Adam, Bob, and Carl, and then here multiplied by the payoff. So these are these matrices MI. And now we have to solve a system of 3 quadratic homogeneous equations in the 8 tensor entries P, I, J, K. So the Spawn variety lives in a 7-dimensional projective space or in a 7-dimensional simplex, and it's given by 3 quadratic homogeneous equations, namely these equations. Well, let's look at the subset of Nash equilibria. So the way we do this is we intersect with the Segre variety. And I put this up. This is copied from the book. So I said 20 years ago, I had this book on solving systems of polynomial equations. That was when the movie was made, the Nash movie. And so there was a corollary 6.3 in the book that says the set of totally mixed Nash equilibria for such a game, a 2 by 2 by 2 game, consists of the common zeros. So little a, b, c are probabilities strictly between 0 and 1 of 3 bilinear equations. And what's happening here is that you take this these p, I, j, k, and you just write them as rank 1 tensors. So P111 is a little k, lowercase a, b, c. P112 is a times b times 1 minus c. And then P121 is a times 1 minus b times c, and so on, right? And P222 is 1 minus a times 1 minus b times 1 minus. So I'm just parameterizing the positive Segre variety. And then I have these 3 bilinear equations. And they have 2 solutions. System of 3 bilinear equations has 2 solutions. And you go back and read Nash's originally works on the same paper in the same year he published. He wanted to show, Nash was very interested in the loss of linear ease, and he published a little paper called A 3-Man Poker Game. So the 3-man poker game, you had to solve the quadratic equation. He got this kind of system and he did everything by hand, and he showed you really have a non-rational, irrational point. So in those days, the games were things like poker, and they were played by people like men. Okay, so the Spawn variety, here's the first theorem. Okay, so let's fix generic payoff tables X. So again, I'm fixing n-dimensional real tensors of the same format, and I'm assuming that they're general, so they're random. Then the Spawn variety will be an irreducible variety of the expected codimension. So the expected codimension here is d1 plus d2 plus dn minus n. And that's the expected codimension because the ith matrix inflicts di minus 1 constraints on the system. Now, the first question you ask about any variety is the dimension. The second question is what is the degree, and the degree is also the expected degree. It's d1 times d2 times dn. Now, we talked about Bach and Stravinsky. So for a 2-player game with 2 choices, our variety is a quartic curve in 3 space, and that's an elliptic curve. Elliptic curve, a non-rational variety. In all other cases, the Spawn variety is rational. And so here I summarize this. So it's represented by a map that maps it onto an n-dimensional space, P1 times P1 times P1. I'll explain this with linear fibers. So there's sort of a geometric reason why this is rational, except in the Bach-Stravinsky case. So So for example, here in this case, I have these 3 quadratic equations in P7. So I have a 4-dimensional variety, but this 4-dimensional variety is rational. There is a rational parameterization. And so you can parameterize all the dependency equilibrium by a process that I will describe. Okay. So this is the theorem. So nice, so rational means nice. There's a parametric representation. Okay, so let me explain this map. So is there maybe, are there any questions about the statement? The first sentence should be clear. So I'm telling you, for generic data, everything is as expected. An irreducible variety and the degree and the dimension are what you expect. But then there's sort of an interesting distinction that in the tiniest case, we have a non-rational variety, an elliptic curve, but in all other cases, we have a rational variety.
Can you say when something is generic? I mean, do you have the equation of non-genericity?
Well, there is a discriminant. We haven't studied. Right? So there will be, as always, so in this space of payoff tables, so there's this space of instances that has dimension n. It has dimension n times d1 times d2 times dn. So in this big space of tensors, there will be a hypersurface. And this is the discriminant where it's not generic. We haven't studied this, and this was the first paper, but I think it would be very, very interesting problem to determine the degree of this hypersurface. And for Ilya, the degree is a polynomial in one variable. So this discriminant has a degree, and I don't know what it is. Yes.
I have a question. Are the real points dense in the context one? Makes sense for keep in mind of your problem.
So that is a very good question, and I think the answer is yes, under mild hypothesis. And the reason is the following. So there is a real point. That's already by Nash. So that's not quite true, but let's say there's a real point in the interior. Then if this real point is non-singular, then the real points will be dense. So if it's an irreducible variety, and I have one non-singular real point, then it will be real. So I think one can show this with under mild hypothesis.
Yes. In the previous example.
That's true. Okay, so let me talk about this rational parameterization because this is interesting. It's the so-called payoff map. So let me recall that the expected payoff for the ice player is the dot product of the tensor P with the tensor Xi. So I mean the scalar product between the vectorizations of the two tensors, and let me call this lowercase xi for a moment. So then for any point on the Sporn variety, in particular for any dependency equilibrium, then this vector xi -1 is in the kernel of the tall skinny matrix. Right? That's almost by definition. So what I wrote in the first columns were the denominators. What I wrote in the second column were the numerators. Well, xi is the ratio. So therefore, this vector is in the kernel of this tall skinny matrix. Right? So now I'm going to find the payoff map. The payoff map takes a solution, it takes a point in a Sporn variety, and simply maps it to the vector of payoffs, x1, x2 up to x for the ith player. I'm going to write this in the way a geometer would. So I take the Sporn variety and the xi coordinate. I think of this as an affine coordinate on a projective line. So this P1 times P1 times P1. So each projective line P1 is the payoff, it's the expected payoff line for the ith player. I'm going to write it like this. I'm going to map P the vector kernel and then because this is the kernel. Right? So I simply think about this column as a point on the projective line with on this affine chart. Okay. So okay, as I said, so Zi is going to be homogeneous coordinates for the ith line. So the payoff map takes a tensor variety onto the product of the payoff lines. So now I'm going to do this. Here's the only trick in the whole talk. So I'm going to rewrite this equation. So I have this equation MIP times ZI transpose, linear in ZI, obviously, but it's also linear in P. So I'm going to rewrite this. Right? I have a system of bilinear equations. I can write this as a matrix times vector in two possible ways, right? Now I'm going to make a very, very, very long column vector, and there's a small matrix called KXIZI. So this is the same bilinear equation, but here I just, I switch the role of P and Z. Now, what about this matrix? So this matrix KXIZI now has DI rows and has lots and lots of columns, D1, D2 up to Dn, but its entries are now binary forms, homogeneous polynomials in two variables in the ZI. And the tensor here is thought of as a long column vector. So this is the matrix Ki, and I'm going to stack these Ki's together. So each player, first player, has first matrix up to the nth player, and I'm just writing them one on top of the other matrix. Okay, so this constants matrix, the number of rows is the sum of the DIs, and the number of columns is the product of the DIs. Okay, so this is the constants matrix. We'll see some examples. So here are a couple of observations, right? So the rows, number of rows is the sum of the DIs. If Z is generic and the kernel is simply as expected, the number. Now with this new notation formulation, the small the payoff. I say Z1, Z2, I look at these players, how much do you want to get paid, right? I make a vector Z1, Z2, and then I look at the kernel, and this gives me a linear subspace contained in the Sporn variety, and the Sporn variety is the union of all of these linear subspaces. Okay, so let's see an example. So this D is the kernel dimension, right? Now we have to distinguish two cases. So either there is no kernel, so capital D is 0, or there is a kernel, right? So if there is no kernel, that says that D is equal to 0, right? So how can this happen, right? So I have a bunch of integers whose product is equal to their sum. And these are integers bigger than 1. Okay, well, there's only one case. That can only happen if everything is 2, right? The only way you can have a bunch of positive integers bigger than 1 multiply to the same thing as they sum to is if it's 2 plus 2 equals 2 times 2. So in this case, here's the constants matrix. So here, the first two rows are comes from the payoff for the first player. And the second two rows comes from this. So here it's a 4x4 matrix. This is general, for general pay for everything is general. This is invertible, right? But now the determinant of this is an equation of degree 4 in the x's. But really, you can see x1 is only in the first two rows. That's the expected payoff for the first player. x2 is the expected payoff for the second player. So we should really think of this as a curve of by degree 2, 2. There's a curve of degree 2, 2 in P1 times P1. And that's our elliptic curve. That's the same as the elliptic curve. So the payoff map gives a birational isomorphism upstairs from our curve in P3 to this plane elliptic. So this is the case when the variety is not rational. Now, as soon as there's a kernel, then I get lots of linear spaces on the Sporn variety, and that sweeps out the Sporn variety. So in this case, the payoff map is dominant onto. The generic fiber is a linear space, namely the kernel, thought of projectively. And therefore, the Sporn variety is birationally equivalent to a product of projective spaces, so the kernel times the payoff space. Right? So this is the proof. And the representation So we have the Spohn variety, person in Constance, and the Constance matrix, city in the south of Germany. The next slide is called Philosophy Meets Delpezzo. So let's go one step higher. Let's say we have a two-player game, and the first player, so the second player still chooses Bach or Stravinsky, but now the first player says, you know, do we take a car or the tram or the bicycle to go there, right? So the first player has three choices, and the second player has two choices. So this is the only time the kernel can be one-dimensional, right? So now capital D is 1, right? So I'm interested in a bag of integers bigger than 1, such that the product is bigger than the sum by 1. Okay, that happens if I take 2 and 3. Now here's the Constance matrix. So for the first player, we have 3 rows. So we organize the payoff table for the first player in the 3 rows of the Constance first rows. The second player, we have two rows for the B's. So this is now a 5 by 6 matrix. So this does have a kernel, always has a kernel. And the kernel is always one-dimensional, except at 6 special points. So given, so the A's and B's are given. So I claim in the x1, x2 plane, there are precisely 6 points where the rank drops further from 4, 5 to 4. Now here's the inverse map. Right? Remember, I had the inverse map that parameterizes the Spohn variety. Right? So I have my payoff plane. Right? So this is the payoff for the first player. This is the payoff for the second player, and I map to the kernel of the Constance matrix. So this is a map to P5. Right? The kernel is a vector of length 6. So I'm mapping to P5, and this map blows up the 6 points. That's the blow up of 6 points here in this space, and the inverse is the payoff map. So conclusion in pink to the conclusion for algebraic geometers. So in this case, the Spohn variety is a nice rational variety. It's a so-called Delpezzo surface of degree 2. So if you're making a Delpezzo surface of degree 2 by blowing up 6 points in P1 times P1. Now, for everybody else, right, the payoff values determine a unique equilibrium, right? So in this case, when capital D is 1, I'm saying I have a one-to-one correspondence between the payoff pairs and the points in the Spohn variety, right? So if you give me x1 and x2 in the play, if you want this payoff, so x1, the first player has payoff 5, second player has payoff 17. There will be a unique point in the Spohn variety, a unique dependency equilibrium, unless I'm very unlucky and the 2 payoffs you gave me are at these 6 special points, in which case there's an entire line in the Spohn variety. So this is the next case. So we saw one curve and we saw one surface. Let me talk a little bit more about the real geometry. And so the image of the set of dependency equilibria under the payoff map, I'm going to pay the payoff region. So I talked mostly about this complex variety, but now let's restrict to the simplex. So these are the actual semi-algebraic set, the actual dependency equilibria, and let me map this now into Rn. So I'm going to go to the affine chart on my product of P1s, and this semi-algebraic map I'm going to call the payoff region. So the payoff region are tuples of real numbers that I can actually get as payoffs from a dependency equilibrium. Actually pay. Okay. Now for 2 by 2 by 2 games, so here's sort of the picture, right? So the projection of the simplex. So if I project the simplex under the payoff map, I simply get the convex hull of the tuples of matrix entries, right? So I make the vector of corresponding tensor entries for all the possible outcomes. I draw the convex hull. So in Bach and Stravinsky, this convex hull of 4 points is actually a triangle. But then the image of our dependency equilibrium in this example is this light blue line segment, right? It's the image of this black line segment. And then here is Nash somewhere, okay? Now this gets a little bit more interesting in the Del Pezzo example. So let's go over this. So we have two players. The first player has three choices. So player A has three choices. Player B has two choices, right? So I have a 3x2 payoff table A, and I have a 3x2 payoff table B. I draw this as 6 points in the plane. I take the convex hull and the convex hull, the 6 blue points. So I take these two payoff tables, I draw them in the plane, I get this yellow pentagon. And now in the yellow pentagon, it's subdivided by algebraic curves. And the payoff region is this curvy triangle together with this curvy triangle. So this for a particular choice of A's and B's, I claim if you pick payoffs here, then there's actually upstairs in the 5-dimensional simplex an actual dependency equilibrium. Right? Now, because this is a birational map, if Giorgio picks a point here, there will be unique dependency equilibrium upstairs. Except this point is special. Right? At this special point, there will be an entire line. There will be a line segment. Right? So I have a bundle of polytopes. So in complex geometry, I have, this family of linear spaces sitting over there. But of course, if I restrict to the real positive domain, I have a bundle of convex polytopes over the blue region. Right? So what I describe is a bundle of polytopes, and generically, this is a zero-dimensional polytope, also known as a point. But then here, this Del Pezzo blow-up says there's actually a line segment. So this is the payoff region. Now, Spohn and the philosophers, they were very, very interested in points out here. So they're very interested in Pareto optimal points. So the Pareto optimal means that payoffs are sort of far out there to the upper right side. So the reason we got into this is because they asked us about Pareto optimality. Here's the second theorem of the talk, and this concerns the real geometry. And I'm going to throw in oriented matroids to this statement. So my second theorem says the payoff region for a generic game is a union of oriented matroid strata drawn in R to the n. Now, what are these oriented matroid strata? They're given by the signs of the maximal minors of the constants matrix. So here I have this constants matrix that I defined for you in general. This constant matrix has more columns than rows. It has a kernel. So now I can look at the maximal minor. So each maximal minor is a polynomial in the axis. And this polynomial in the axis defines a curve or hypersurface in the payoff space. Right? And then the regions that are cut out by the signs. Each of these polynomials can be positive or negative or zero. So this stratifies R to the n. And this is the stratification you saw in the picture. Right? So these maximal minors give us various curves. And then on each of these regions, each maximal minor takes a certain sign. These are called oriented matroid strata. Now we're interested in the boundaries. So the boundary is a union of irreducible hypersurfaces. And the degree is a little bit smaller than expected. So the degree is at most the sum of the di minus n plus 1. So this theorem kind of delineates this stratification of the payoff space, and it tells us the algebraic degree of the boundary of the payoff region, therefore gives us information about Pareto optimality. Where do we have to go to find Pareto optimality?
So your genericity is a different genericity, not the one that.
No, it's genericity for the game. So X, so the instance, so generic here means.
So as soon as your Spohn variety is reducible, the one that you are in theory about this.
Yeah, so let me simply assume here X is really completely generic, right? So that means the A's and the B's are random. In this matrix, the A's and of course, if the A's and B's are very special, then this picture will degenerate as special. So generic here means the A's and B's are somehow random. Does that make sense?
So it's not enough to assume that you're right up there.
Is it? No, you probably need a little bit more. So we haven't really, so as I said, we haven't really, looked at the degenerate situation in general. We haven't computed and we haven't studied the discriminant. This was really the very, very first paper. So lot more to do. Okay. Let's briefly talk about Adam, Bob, and Carl. So I promised Ilya that I'm going to say K3 surface in this talk, and I will on this slide. So let's look at 2 by 2 by 2 games, right? So now the constants matrix is this 6 by 8 matrix. So the first 2 rows are for Adam, the second 2 rows are for Bob, and the last 2 rows are for Carl. Now, according to the theorem, we should look at the 28 maximum minors. That's I guess that's 8 choose 6. In this case, the irreducible polynomials of degree 4 in 3 variables. So I have 28. My stratification is given by 28 surfaces of degree 4 in 3 space, and a surface of degree 4 in 3 space is called a K3 surface. So the analog here, so I just go up by 1 dimension. Here I had this arrangement of curves in the plane. Now I have this arrangement of 28 K3 surface. So I get an arrangement of quartic surfaces. So these constrain chambers inside the polytope. So there's going to be a 3-dimensional yellow polytope that just is described by the payoff, which has at most 8 vertices. And this can be studied. So I don't have a picture, but since I only have 3 minutes left, so a quiz, for philosophers, what does all of this mean? Right? So we're in discussion with Spohn, and of course they think about this very, very differently. What's an oriented matroid anyways, right? And it's a strange concept from combinatorics. Well, questions for mathematicians, sort of a quiz, right? What was the dimension again? What was the payoff map? And what was the payoff region, right? So this would be, if this were a course, this would be a good moment to recap what actually happened. Now I'm going to close with a quick remark about statistical models. So Francis emphasized the importance of probabilistic inference in statistics. So let me now restrict well-studied, interesting varieties in tensor spaces. And so in our last section, we're intersecting the Spohn variety with the conditional independence variety. Now, if C is the set of all conditional independent statements, if every conditional independent statement holds, then we have complete independence, then we have Segre, then we have Nash, right? So if everything holds, then these are the Nash equilibria. But this gives us a way to stratify very nicely between Nash equilibria, where all players are independent, and dependency equilibria, where we have complete dependency. So we can say, Hamza is independent, of Bernard, given on Giorgio's choices, right? So we can do that. The number of here's the number of solutions for the games, actually very nice. The number of arrangements from your first discrete math course. So beyond Nash, we looked particularly on Bayesian networks, and we looked at the model with one edge. This was already interesting. So we just went one step away from complete independence. We have these n players, if everything is independent, you have Nash, but now let's just say 2 players can interact. That's all, right? And binary choices. So then, the conditional independence model is this partial Segre variety. Now the Spohn variety that's intersected is a curve, and this was studied in much detail in a follow-up paper by Iram with Javier, who's a postdoc, that presented this at the Mega conference. And in the meantime, they have a very nice generalization. So let me conclude. What I presented is a new direction at the interface of game theory. And in the last minute on algebraic statistics, there are lots and lots of open problems of all kinds in this. I'd love to talk to you. And as a side remark at the end, so in the probabilistic inference, causal inference is a very, very important topic. So I'd like to end with the remark that also in causal inference, Wolfgang Spohn was ahead of his time. So he published a paper 30 years ago called 20 years ago called Dependency Equilibria and the causal structure of decisions and game situations. So at that time, he talked about Bayesian nets and the relation to these equilibria notion, and many of the concepts that you now know from causal inference, say a work of Judea Pearl and others, was foreseen in the work of Spohn. So for me, this was very interesting, and I found this kind of an interesting golden. So this is the end. Many thanks for listening.
We have time for one or two questions.
So in this classical situation, you mentioned you're in a sparse situation, like McKelvey, McLennan, and so on. And your use situation, the conditional situation, you're not in a sparse situation because you have the expected degree and so on. The question would be, can this also help to understand the classical situation?
Yeah, well, okay. So here, yeah, so what Torsten is saying, so let me advertise it again. So if we have binary choices, so there's generically there's a finite number of Nash equilibria, and then you have the number of players. It's like 1, 2, 9, 44, 265, which you know from your discrete math class. Now, of course, in these other situations, there's not a finite set, but you still have sparsity. You still have sparsity, and you have special structure. So we chose here to encode the special structure in this matrix form. Right? So this constants matrix sort of carries the special structure in this case. But of course, if you throw in, conditional independence, and basically you have to. So we're looking at tensors whose vectorization is in the kernel of this matrix. But now, of course, we're saying this tensor here
there are no equilibrium points.
So okay, well, so Nash is of course the smallest, right? So Nash is the smallest, right? So this is a nested family. So I have this poset of all conditional independent statements, and the smallest one is Nash. Now again, let me say about Nash. So Nash proves that there is always at least one Nash equilibrium in the closed simplex. It could be on the boundary. Okay. Now this whole discussion here is about what happens in the interior, right? Now, if you're on the boundary, that's where the combinatorial complexity goes, right? So if I knew I'm on the boundary as an algebraist, I would just throw out a choice and work in that simplex, right? So I would say, well, if it's in the boundary, then let's focus on that simplex and do an algebraic analysis in that simplex. But of course, in computer science and in game theory, it's the combinatorial complexity is also very, very important. But if the Nash equilibrium is in the interior, then of course all of these are non-empty over the real numbers.
All right. So I just have a maybe a silly question, but when you look at your variety, you have an elliptic curve, but over reals, elliptic curves come in two types. They either have one connected component or two connected components. Does it happen that, or generally these things have different real structures, even though for complex?
Yeah, so we have cases where we have one or two connected components. We haven't completely analyzed all cases, but this would be doable, right? So we have this elliptic curve in 3 space. Now there could be one component or two components, and now we have to ask, how can this intersect the tetrahedron, right? So we have done a little, we didn't work it out completely, but this would be doable in this space.
But also for other more complicated, and now they have more different real structures, and how these real structures vary.
I mean, what can I say? I mean, let's hear, where was Del Pezzo? We had Del Pezzo somewhere. Okay. I mean, the study of real forms of Del Pezzo surface is a very, very interesting topic. Christine Shaw is an expert on this in Oslo. So that's already a very interesting topic, is what are the possible real forms that you can get? there is a restriction. So we don't get all surfaces. So there's already a restriction, right? So there's a moduli space of these. There will be some restriction, and I don't know what the restrictions are. But then even if we have the real structure, then the question is, how does this intersect the simplex? And how will this intersect our simplex? I think it would be very interesting topic to study.
Maybe last question, Giorgio.
Thanks. Please, can you go back to the slide where there are the sign of the determinant of maximal minor, the oriented matrix? Okay, that's one. So if I understand that the maximal minor gives strata, depending on the sign on the two chambers, maybe let's go. But do you know if on the real all possibility of sign can be attained? Really, maybe not. No, there should be some obstruction.
Yes.
I mean, if I say plus plus minus minus plus is maybe empty or
Yes. So there's an answer at two levels, right? So the first level is just take any matrix whatsoever, any real rectangular matrix. What are the possible signs? So this is the study of oriented matroids. So matroid theory tries to characterize which minors can be zero and non-zero by some axiom system. An oriented matroids over an ordered field aims to characterize the signs. There's possible sign patterns, and there's a whole subject. There are books on this. So this is oriented matroid. Now, but here I don't have a general matrix, right? Here I have a matrix that's highly structured, right? This is a very highly structured matrix. So I think it would be very interesting to study the additional constraints on oriented matroids coming from the structure of the constants. I think it would be very interesting. So if I just say, right, fill the entries the way they're indicated here, but keep the zeros, what further restrictions does this impose on the systems? I don't know.
Okay, we have a very tight schedule. Let's thank Bernd again.